So now that the basics are covered in both least squares and error propagation, let's do a version of least squares that's called weighted least squares. And over here we've got 3 leveling routes between a benchmark and unknown point. And this is 3 kilometers long, 2 kilometers long, and 4 kilometers long. And weighted least squares assigns weight to each measurement, and the higher weight means that the measurement is more precise. Usually in leveling, the longer the leveling route is, the result is going to be less precise. That is, it's more error prone. There are more chances for mistakes. And one way to select the weights for each of these routes is to take a lowest common denominator type value, and that would be 12. Because 4 times 3 is 12, 2 times 6 is 12, and 3 times 4 is 12. And there's no one perfect way to create a weight, as long as it makes sense and as long as it's consistent. Any type of weight can be used. And weights are usually represented with a P or a W. Over here we're going to have 6 measurements. 2 measurements for route 1, 2 measurements for route 2 there and back, and 2 measurements for route 3. And the shortest distance gets the highest weight. So the shortest distance gets a weight of 6. The second shortest, or the middle distance, gets a weight of 4. And the longest distance gets a weight of 3. And again, we can take this is just one way to do it. Another way would be to take the inverses of the distances, and still that way the shortest distance would get the highest weight. In that case it would be just 1/2. This would be 1/3, and this would be 1/4. So the longest distance would get the lowest weight if we take the inverses of the distances. And again, it's going to slightly change the result, but again, as long as the weights are consistent, or the weights make sense, that's all that matters. So we have 6 measurements, and we're trying to determine HB from HA. And these are the 6 measurements. And so this is obviously an overdetermined system, because one measurement would be enough to measure the elevation difference. So our redundancy here is 5. And in least squares, we have to write down the measured as a function of the unknown. This is the generic leveling equation. That is HB equals HA plus little h. And we have to rearrange this so that we write down the measured as a function of the unknown, That is, each measurement, H1 is going to be equal H1, H2, H3, H4, H5, and H6 are going to be equal to HB minus HA. So this is HB. H5 and 6. So our P matrix, or our weight matrix, are 4, 4, 6, 6, 3, 3. And there are 6 measurements. And HA is equal to 0 meters. And the question is, what is HB with the weighted solution, and what is sigma HB going to be after the weighted solution? So we have to write down each measurement as a function of the unknown for least squares. So it's going to be the same for all these, and again, it's always implied that there's a residual. And then we have to take the Jacobian with respect to the unknown. So the Jacobian with respect to the unknown, or the partial with respect to HB, is just going to be 1 for each one of them. So this is the generic setup: A transpose A inverse A transpose Y. For the weighted, we just put the weight matrix in the middle. And the weight matrix, if we actually write it out, so these are the individual weights, and our weight matrix, so this should be little p, this is big P. The weight matrix is going to be just a diagonal matrix, where the off diagonals are zeros. And the order is the same as the measurement order. So X adjusted is A transpose P A inverse A transpose P times Y. And our y is the vector of the knowns, so this is already separated into knowns and unknowns. Oh, it's not separated, I'm sorry. So we have to rearrange this to separate it into knowns and unknowns. So we'll separate this into knowns and unknowns. You just have to take HA onto the other side. So H1 plus HA is equal to HB. And again, there's the residual. So H2 plus HA is equal to HB. And so on. H6 plus HA is equal to HB plus V6. Then take the partial with respect to the unknowns. That didn't change because of the way the equation was set up. And then all we have to do is plug it back into this weighted equation. And we can do that in Octave. So there's our Y matrix. And then we can use the diag command. To create a diagonal matrix out of it. And that's it. So now we can calculate the adjusted value. A transpose times A inverse times A transpose A inverse. Oh, I forgot the most important part. That would be the P matrix. Or, well, not the most important, but A transpose A inverse A transpose should be a Y. So all we did was put a P in the middle of it, the P matrix into the middle of it, and it's 4.4525. 4.5425. So now we know that, so now we can calculate the standard deviation of HB. And all it is just let's just use, first we calculate the covariance variance matrix. For the posterior adjusted value, sigma 0 squared times A transpose P A inverse, where sigma 0 squared is equal to V transpose P times V divided by the redundancy. So this is the standard deviation for the entire system. V is the individual residuals. And we can calculate V as A times X adjusted minus Y. So V is going to be equal A and the residuals are small, so that's what we're looking for. So our sig 0 squared is going to be equal to V transpose divided by the redundancy, which is 5, We have 6 measurements. 1 would be enough. So the redundancy is equal to the number of measurements minus the number of unknowns. 6 minus 1 is equal to 5. And again, the covariance variance matrix. For a covariance variance matrix, the diagonals are the variances. In a 1-by-1 matrix, that represents the variance of the unknown value. So we're going to have to take the square root of that. So the standard deviation, or sig HB, so sigma HB is going to be equal to the square root of, in this case, of sigma post square root post. If there were more values, that is more, if it would not be a 1-by-1 matrix, but say a 2-by-2 or 3-by-3, we'd have to put the appropriate index, like if it was the third value, oh, here it is, 3. So if it would be the third value, it would be 3, 3. Or we can also specify it this way, in this case 1, 1. That is the first row and first column. 0.0, basically 0.002. That equals 0.002 meters. So this is how a weighted least square solution is done. Now, of course, if we'd use different weights instead of these, like the inverses of the distances in kilometers or miles, the first two would be 1/3, then 1/2, and then 1/4. No, it's make it a little bit smaller. One-third, 1/3, 1/2, 1/2. We get slightly different results, but the weight, since the weight ratios are not going to be the same, but still the second root has the highest weight, the first root has the second highest, and the last one has the lowest weight. So in this case, that's all that matters, and again, there's no one perfect way to do this.